Oh, okay. So our next keynote speaker is Mark Russinovich. I should tell you that I don't know him. I met him for the first time this morning. But Albert Greenberg, whom I know very well at Microsoft, he's the one who suggested I invite Mark. And then I did some research on Mark, and I found out that he is an amazing guy in terms of the diversity of things that he does and how much hands-on person he is. I was looking for one particular phrase using which I can describe him, and the one I could come up with is he's a prolific author, in the sense that he's a prolific author of software himself. He has contributed a lot to system internals. If you don't know about it, you should check it out. When I was doing research on Mark, that is when I learned about it. He has written articles and books about Windows architecture, internals and all of that. And he has also written novels, high-tech thrillers. And also he is very amazing in terms of doing investigation of security vulnerabilities, primarily in Windows. And so he has a lot of number of accomplishments in that area as well. So you can see he's a person of very diverse talent, and really delighted to have him. So Mark, please come and share your thoughts. Okay, cool.
Thanks, Guru. All right, let's get started. My name is Mark Russinovich, CTO of Microsoft Azure. I've been in Azure for about 5 years. And as Guru said, Albert Greenberg spoke here last year. I'm speaking this year. And a lot's changed in the last year. Key change, which, if we get the slides up on the display, you'll see right away, is that last year, probably the biggest change. Last year, it was called Windows Azure, and this year it's called Microsoft Azure. So huge changes in the public cloud. And Albert gave a talk last year about how we use SDN in Microsoft Azure. And unfortunately, I'm going to have to tell you that everything he told you we've learned is wrong. And so this talk is about redefining everything. No, I'm just kidding. What I'm going to do this year is to go a little bit deeper into some of the areas that Albert talked about. And I'm going to start by talking a little bit about the scale challenges that we've got in Azure, which is a good challenge to have. I'll represent that in a few different ways to show you just what it means when we say hyperscale public cloud and the requirements that drives into network specifically, which will lead us right into how we build a hyperscale software-defined network. And then some key challenges specifically in the network area, specifically around how to make a hyperscale controller or controllers, and then how do you make a hyperscale host as part of that software-defined network solution. So I'll start first by talking a little bit about Azure. Let me get my clicker going here. How many people have used Microsoft Azure? Just raise your hands. Okay, this session's being live streamed, so the people watching can't see how many hands were raised, but I think everybody in the room raised their hands just now. For the people watching, I'm just kidding. Well, so Microsoft Azure has been around, like I said, for a while, and it consists of a growing number of services. In fact, I've just showed you a subset of the services here. We tend to divide it into various layers of services that you can enter the platform at. At the top level, there's application services, so we have things like identity management, and we've got websites as a service, or web apps. In the middle layer, we've got a whole bunch of data services. We've got, of course, database as a service. We've got a new service called Data Lake, just to give you an idea that we're releasing data as a service, applications as a service all the time. In the last 12 months alone, we delivered over 500 new features and services into Azure. And at the very bottom of the stack, of course, we've got the infrastructure, which includes virtual machines, virtual networking, and storage. In terms of the scale, and in terms of the usage of Azure, all of Microsoft is making a massive bet on Azure. So of course it's a public cloud, but it's also our internal cloud for our own resources. We build much of our infrastructure, much of our services that we deliver to customers, including Office 365 and Skype and Xbox, on top of the Azure platform. And to deliver those services to our customers, we've got data centers all over the world. If you take a look at the growth of our data centers, in 2013, this is what our regions look like across the various geographies in the world. In last year, we introduced a number of new regions. So this is new since Albert talked last year here. And then we've got a couple new regions coming online in the next few months in India. And of course, there's a number of regions that we're working on that I can't talk about yet. If you take a look at the growth in terms of capacity, from 2010, when Azure launched, to now, the number of compute instances or virtual machines has gone from around 100,000 to the millions. In terms of Azure storage capacity, it's gone from tens of petabytes to exabyte level capacity. And in terms of the data center network itself, we've gone from tens of terabits to petabits of capacity in our data centers. And speaking of networking, let's take a look at the networking growth. If you take a look, one of the things Albert talked about last year was how we launched something called ExpressRoute, which was launched at preview right before Albert came here and talked. Well, we've had amazing growth of ExpressRoute. So we've got over 20 ExpressRoute locations around the world, more than 24 partners, including, proud to say, down there, AT&T is one of them. We've got 1,600 peered networks in over 85 internet exchanges around the world to allow customers to peer from their networks into our networks. And if you take a look at some of the scale momentum we've got, here's a bunch of different statistics just to throw at you to give you an idea of the scale at various levels of our architecture. Over 57% of the Fortune 500 is using Azure. We've got, here's some of the more striking numbers on this slide. We've got an eventing service, an event ingestion service called Event Hubs. They're on the top right. Last month, we hit the 1 trillion events ingested in the month. If you take a look at our Azure storage service, I mentioned it's an exabyte scale. In terms of number of objects, we've passed 50 trillion objects. That number was 30 trillion last September, just to give you an idea of the kind of growth we're seeing. And then we're also seeing growth and adoption, not just from the traditional Microsoft customers, but from cloud software vendors, as well as the non-traditional Microsoft customer. And if you look at that number right there, over 20% of the virtual machines running in Azure are Linux. How many people run Linux, just out of curiosity? All right, there I get almost everybody to raise their hands. So it gives you an idea of the kind of scale that we're dealing with in Azure. Now, to build a network for that kind of scale, of course, we've turned to software-defined networking. This isn't new. We had to break out of the proprietary appliance, control data plane, management plane, all combined together in vertically scaling, very fragile, very inefficient, and kind of inflexible devices to go to software-defined networking, where we break these things apart. So we've got management plane, which exposes APIs. We've got a controller or control plane that takes those APIs and then creates rules and then plugs those rules down into the switches, which are on the host themselves. For example, when we create a virtual network, what we call a tenant in a collection of virtual machines that are connected with virtual networking rules, that was a layer of abstraction exposed up through those APIs, and that is translated into ACLs and routing rules that are then plumbed down into the hosts, where those routing rules are executed just on the hosts that are relevant for that particular tenant, where that tenant's virtual machines happen to be running. That's the only way we can get to the kind of scale that we do. The key here, Albert emphasized this last year, I'm emphasizing this again because we're going deeper here, is host SDN, where we push as much of the logic and processing down into the host. So let's talk a little bit about building the hyperscale controllers. How do we do that? If we take a look at the kind of scale that we have within one region, and we've got a regional model in Azure. We want regional isolation for disaster recovery and high availability. So when we talk about networking, we talk about per region networking. And we've got controllers then that operate on the regional level. Well, the regions that we've got in Azure and some of our mega hub data centers or regions, collections of data centers, are approaching the 500,000 server or host range. And so we can't scale many of our controllers to manage the logical resources that are deployed onto that kind of infrastructure, that kind of physical infrastructure with a single controller. But we've got to scale up to those sizes, but we also have to scale down to very small sizes as well. When we go into new regions that are very small, we don't want to spend a lot of our infrastructure on overhead for running our services. And so we need to make sure that our controllers can scale down to very small sizes as well. We also have to handle enormous amounts of traffic and updates. So the controllers have to be very efficient, and they've got to be able to scale out to handle many requests concurrently coming from many, many different customers. And we also have to be updating this constantly. Part of operating at cloud scale and operating in a services world is being able to update the controllers all the time, whenever we want to, not just for updates, but also, in some cases, when we roll out an update that has a problem, be able to repair that update quickly. And we need to do those kinds of updates without causing any downtime to the control plane. So what we've done in Azure is take a partitioned approach and a tiered approach for our controllers. So, for example, to handle that 500,000 type scale in a particular region, we've got a regional controller. And this one is partitioned and consists of subservices that are related to the controller's functionality. But then that is where the source of truth is stored. So that is where the definitive state for the controller is located. But then we delegate work down to a cluster level, which is around the order of 1,000 hosts or servers. So the regional controller will push information down into the cluster controllers. These cluster controllers are effectively stateless caches. They can fail and then relearn the state for their cluster from the regional controllers. But that means that at the cluster scale, operations can be served right from the cluster controllers down to the hosts themselves. And that's where we've got network agents, which are proxies of these controllers that are then talking to the switches, the logical switches that are implemented in software on those particular hosts. Now, to get this kind of agility that we want in creating these controllers and being able to scale them out and partition them, we're using a technology we've developed internally at Microsoft called Microsoft Service Fabric. Service Fabric is a microservices application platform. And it's one that we've developed over the last 10 years and been using in production for the last 5 years across Microsoft services. I'll talk more about that in a second. But essentially what Service Fabric is, it's a microservice-based application platform that takes care of all the grunt work of application lifecycle management for an application that is decomposed into microservices. And it's available for operating in Microsoft's public cloud, for operating in private clouds, and even for operating and serving as a platform in non-Microsoft clouds. And I'll talk more about that as well in a second. If you take a look at the capabilities that it delivers, it is a cluster orchestration and application model as well. So the model is declarative. So we declare our controllers using a declarative model that specifies what microservices they consist of. And we also declare a number of constraints and requirements that Service Fabric honors as it operates the microservices. So you can see some examples here that we can specify the number of update domains. So when we do rolling updates, we're only taking down slices of the microservices, implementing a service functionality at a time. It supports rollback. So this is required for being able to operate reliably. So if there's a problem, Service Fabric can roll back the update automatically. It supports leadership election, which is important, of course, for stateful services like our controllers, because we need a system that keeps track of the state and replicates the state to other systems, but needs to know which one is the primary, the master state. It supports name discovery, of course. The microservices need to be able to talk to each other and talk to other applications. I mentioned it supports partitioning. It supports load balancing and other constraints for migrating and microservices from one host to another. And I mentioned the key thing here for us in building these kinds of controllers is that it supports stateful microservices. In other words, microservices that are hosting state and managing it on their own, not externalizing it to an external database. The buck stops someplace when it comes to state. And a great example of that is in our Azure database service, which is built on top of Service Fabric, where each database is represented as a stateful microservice that consists of multiple replicas. And all that state replication and tracking the leader and handling failures is all done by Service Fabric. These list is some of the examples of the services that we've built using Service Fabric and are operating in production right now at Microsoft. That's in addition to the controllers and some of the infrastructure services that we're running at the bottom of the public cloud. And you can see that it also includes services that are non-Microsoft Azure services, like Cortana itself, the personal assistant that we offer on various devices. To give you an idea of how Service Fabric works, it separates the infrastructure, defining a cluster of servers or nodes, and you define the applications, which consist of the microservices. So you hand a description of the microservice application to Service Fabric, and then honoring the constraints and the replica counts and the partitioning, it will distribute or instantiate microservice instances to these various servers. If there's a server failure, it will automatically detect that, and as part of the service healing process, reinstantiate those microservice instances that were impacted to other servers, and then if it's a stateful microservice, we'll automatically catch them up with the primary, or if it was a primary, elect a new primary, and then recreate a secondary, and then catch that up with the primary and the other replicas. All of that is done automatically. And when it comes to partitioning, again, to get to kinds of scales that we need, we do partitioning. So we can partition services for scale out, and this allows for efficient use of resources as well as reduces blast radius and allows us to scale up to those values so that we're not hitting a single server with all the traffic related to a region. We partition the API, the application requests, in various ways, and then route the request to the appropriate partition. This is a look at the composition of our regional network manager. So we've got a few of these network managers that we operate on top of Service Fabric. We've got a gateway manager, we've got a software load balancing manager. They're all architected with that tiered approach. This is what each of those tiers looks like when you break it out and look at the microservices. In this case, for the regional network manager, which consists of microservices for a gateway for routing traffic API requests from customers, a VIP, a virtual IP address manager, a MAC address manager, a virtual network manager. You can see the other kinds of decomposition we get here. What this allows us to do is scale each of these independently and update them independently as well. And that is what gives us this agility that we need to operate and deliver features quickly. Give you the kind of scale here in our largest region. This is the kind of numbers that we're seeing out of our network regional manager, network manager. Tens of millions of API calls a day is what that thing is serving. The API execution times for reads, less than 50 milliseconds, and for writes, less than 150 milliseconds. And if you take a look, the deployment footprint for the network manager, the smallest footprint is 5 servers, and the largest is more than 100. And of course, we scale out to handle more load. So our largest regions have more than 100 servers operating the controller. And then you can see here a breakdown of the types of write transactions that the controller is serving. Each one of those write transactions results in a request that eventually makes its way into one of those agents on a host. Service Fabric is something that we use internally, but about a month and a half ago, we released a developer preview of it at our build conference, so you can go download it today and use it. It supports C++ and C# today. It's Java is coming, and Linux is going to come soon. Today it supports only Windows job object containers, but in the coming also, it's going to support Windows Server containers, and of course on Linux, it's going to support Linux containers with the Docker API integrated into it. So this is something that others can start taking advantage of to build their own controllers if they'd like. Now let's talk a little bit about building hyperscale host SDN. What we're relying on here is something called a virtual filtering platform. Albert introduced this last year, and the VFP sits inside the Hyper-V network switch. And so packets, as they flow into the Hyper-V host or out of the virtual machines, get routed through the virtual filtering platform, which applies transforms and rules. So it'll do address virtualization for virtual networks. It'll do a virtual IP address to DIP translation, a physical IP address in the software load balancing layer. This is where our metering happens as well. It supports our 40 gigabit network, so all our hosts now have 40 gigabit network cards, or newest servers do. And this is also something that's going to be coming to Windows Server in 2016. Now, one of the things that we realized, of course, this is a realization in general for host SDN, is that the right abstraction is required to really deliver high-performance host SDN. And the abstraction that we use is a typed match action table API that the controller then defines policy with. The controllers, for each type of policy, there's one table that's processed by VFP. So VFP consists of multiple tables, some of them defined by different controllers. So the software load balancer has its own table where it defines the NATing rules, but the virtual network manager might have multiple tables, ones where it has the ACLs and one where it has VNet, virtual network routing rules, in it. So as packets flow in and out, their rules are processed in order through these tables. These tables go from physical abstraction all the way up to virtual abstractions. And so the processing of these tables happens in order. And what you get as the result is a final action or rule. The key thing here are actions, which can be arbitrarily complex operations, jumping out into the agents, for example, that then might even communicate with the controller. So, for example, if you exhaust the number of ports available for snatting on the load balancer, you might have to jump out to the software load balancer agent, which might even need to go up to the software load balancer to allocate a new range of ports for mapping those address translations for those virtual machines that need it. So there's an example of ACLs and other information being plumbed down from the controllers into the virtual filtering platform. One of the other realizations we've had is that we use connections as the match action primitive, not just flows. So most controllers are really managing a connection, not a flow, and that's the abstraction that we use inside the virtual filtering platform. So an example of why you'd want a connection, not a flow, is that it makes no sense to allow the SYN into a virtual machine, but block the SYN-ACK out because, of course, you're not going to be able to set up a connection that way. Another example is stateful NAT, where you basically want to say, do encap on this or decap on this thing for a load balancer. And what this allows us to do is have a very fast path, bypassing the load balancers themselves and having the host talk directly one to another because that information's all been plumbed down to the host. But we support both primitives because in some cases, some controller rules and policies need to be specified as flows. Now, to get to the kind of scale that we need to get to as we get higher performance networks into our data centers, we've realized that we need to make this processing as efficient as possible. Of course, there's no bypassing the fact on the first packet as a connection is formed that we need to go through these tables and basically go the slow path to figure out what the resulting actions and rules are. But once we've done that first processing, we know exactly what the rules are, and we create a hash table such that based on that connection, we simply do a hash lookup, and we've got the rule that is most applicable. And so that is every subsequent packet then goes that fast path, and we don't avoid complex arbitrary operations, and the rules are very fast and easy to process. Another way that we're optimizing our network and our host, specifically taking load off the host, is by moving to RDMA. Albert talked about this a little bit last year. We're making more progress on this. We're in the process of deploying RDMA into the back ends of our storage networks. Albert talked about how we do erasure encoding. That's one of the things that happens in the background in the storage systems, basically through RDMA on a back-end network, to take load off the front-end network for customer traffic and replication happening at the storage layer. And with RDMA and Rocky v2, which we've made huge contributions to, defining the Rocky v2 protocol, of course, we are able to do this over our converged Ethernet, so no special InfiniBand hardware. RDMA, of course, essentially are DMAing data from one host memory to another host memory very efficiently without involving the CPU at all, completely offloading it. But we've gone a step further. It's not just RDMA. It is actually pushing as much into hardware as possible. And for that, and the reason that we need to do that is because the networks are getting even faster and faster. And if we had to process 100 gigabits networks, which we see is coming inevitably, we can't do that in CPU. And we don't want to do that in CPU. We don't want to process those tables, those connection tables in CPU. And the reason we don't is because we want to keep the CPU for use by customer resources, to serve them. We want to use those CPUs for virtual machines. And then we'd like to offload as much as possible into specialized hardware devices. To do this, we're into our data center something called Azure SmartNIC. Azure SmartNIC is built on top of FPGAs. FPGAs, which we've already been using at Microsoft in our Bing properties to accelerate internet search indexing. Now we're moving this into a more general form as serving the infrastructure for Microsoft properties at large, starting with the network. And this SmartNIC essentially takes that FPGA, puts it in line on the network, and that allows us to, in the FPGA, do network processing, including offloading much of the VFP processing for that fast path directly into hardware. The SmartNIC is where we can do encryption, we can do quality of service, we can do storage acceleration, and a whole bunch of other things. The sky's the limit really here with what we can do, of course, with an FPGA, given how it's flexible programming. If you take a look at how FPGA then works in the world of SmartNIC, we talked about how the rules on that first packet are decomposed into a summary, through a transposition engine into a summary connection table of rules. That is then offloaded into the FPGA using something called the general flow table offload engine. So we've got a general language to specify for our FPGA code how those rules should be executed. That's downloaded into the FPGA, which then essentially does this work of doing things like crypto and RDMA right in the hardware. And with this, we can completely offload all of this complex functionality into this device, saving the CPU. And I've got a demo of that I'm going to show you here. It's going to take me a second to connect into the Microsoft network. So let me do that here. To this machine. And what I'm going to show is, here it comes. So I'm RDP'd into a machine in our lab, and this is actually looking at two servers, two hosts, the one on the left and the one on the right, that have virtual machines on them that are part of a virtual network. And this virtual network is an encrypted virtual network. And what we're going to use is the SmartNIC to offload the encryption into a VXLAN wrapped tunnel between those two virtual machines. But first I'm going to show you the performance of this without acceleration. So if I start a receiver over here, and it's hard to see the screen here. So I'll start the receiver, and over here on the right side, or left side, sorry, I'll start the sender. And this is unaccelerated traffic, so we're going to see the kind of network throughput that we can get just by using the CPU, which is essentially going to be capped by a single CPU, because all of that encryption and decryption is going to have to be handled on a single core. And once we max out that core, we've maxed out our ability to drive the network. And if you take a look, we see that we're able to get, I'm not able to scroll down there, but you see we're able to get just around 1 gigabit per second. So not terribly great, especially because we've got a network adapter on these servers that is much faster than that. Now what I'm going to do is turn on a hardware acceleration. And what this will do is offload those rules into the FPGA. And okay, start up the receiver again. Start up the sender. And here, after a little bit of warm-up, we're going to see, fingers crossed, the demo gods, if I prayed appropriately to the demo gods this morning, we're going to see the, it looks like, might take a few seconds. What's that, Daniel? A what? Oh, I thought I did. I've been told that I didn't run VFP enable on both of them. I thought I did. It's really hard to see the screen. Oh, all right. It's hard to see what I'm doing with the text so small from here, so I apologize for that. VFP enable. All right. All right, let's see. Second try. And there we go. So that's more what we expected to see. It's about 30 gigabits per second we're driving through this, all completely offloaded. And the only reason we're limited to this, and we're still tweaking this, is because we're only able to use the cores on one of the NUMA nodes of this two-socket machine over here on the receiver side, which is capping us and stopping us from getting into 40 gigabits per second, but that is something that we're actively driving towards. So this is an example of how we're able to drive the host network up into the ranges that we need to get to, especially because, of course, we're not stopping at 40 gigabit NICs. We're, as I mentioned, inevitably going to see 50 and higher in the near future. So that brings me to the end of the talk. I think one of the things that you're seeing is that this host networking approach we're taking to SDN is able to let us scale to these massive physical networks, but still get the agility that we need and the abstractions that our customers need from their APIs, and be able to scale out to these kinds of huge kinds of numbers. All the policies and software, everything is a virtual machine based. The network services are deployed like all other services on our network. So we treat all of this as just a software problem, not a hardware problem. And I also mentioned earlier that VFP, other networking technologies like I've shown you here, like the load balancer, are all coming into Windows Server as part of our Azure Stack, which we also announced a couple months ago, which is bringing some of these cloud technologies down for people to be able to deploy into their own networks in their own data centers. So our key lessons here: cloud needs scale, availability, and agility, kind of obvious. But we achieve all three of these for our controllers using Service Fabric and a microservice-based architecture. And we achieve all three for the host SDN with RDMA and FPGAs. And so with that, I want to thank you very much. And I've got some time here for some questions.
Okay, so I guess we may have time for some questions. So, but let me ask you at least one mandatory question I have to ask. As at this ONS, we are emphasizing open source and all of that. You didn't say anything about Microsoft's contribution to open source. I cannot let you go away without saying something about that.
I had a feeling somebody was going to ask that question. So I was actually here just about a month ago at ChefConf in this very room, I think, talking about Microsoft's approach to open source in a panel. And Microsoft is 100% committed to open source in a bunch of different ways. We're using open source a lot internally. We're making open source services as a service, or open source applications as a service for our customers. So for example, our HD Insight service, Hadoop as a service, is built on top of open source, and we've contributed to the Hadoop project itself in collaboration with Hortonworks. We're using our Elasticsearch is. I mentioned that 20% of our VMs are running Linux. As far
Anything
as
in the context of SDN, NFV?
As far as us contributing to open source, we've contributed the .NET Core CLR, for example, is something that we've done recently, released to open source. When it comes to SDN, we're supportive of SDN and public standards and SDN standards. When it comes to us open sourcing some of this technology, this is an ongoing evolution. So we don't have anything planned right now, but we're always looking at this. I think that this is part of the new Microsoft culture, and the question goes before, what is the secret sauce versus what is not? The answer changes over time, and so we'll see where things go.
Okay. I want to allow some time for this question.
Yeah, okay. Raj Jain from WashU. In your host SDN, it looked like more than software-defined, you went really hardware-defined. I mean, like having a specialized hardware. What I've been hearing in the whole forum here is that we want to go for white boxes rather than going for a specialized hardware. But it looks like there is a limit where some things like, in your case, it looks like if encryption really needs the help from the hardware.
Yeah, I think it's a little bit different than a specialized device that is, we consider FPGA really as an extension of hardware because we program it. So it is a programmable hardware rather than a fixed function hardware, something burned and sitting there doing a fixed function. So the reason that we need FPGAs is, of course, for our ability to evolve it over time. But we do see this kind of specialized acceleration as something required to get to these kinds of performance levels.
Okay, thank you.
Good morning. Paolo Verissimo from the University of Luxembourg, in this remote location called Europe. Thanks for sharing this impressive transformation that Azure went through. And this commitment to SDN obviously brings a lot of benefits, but increases the threat surface, the threat plane. You mentioned several redundancy measures for fault tolerance, so accidental faults. And I'm sure that you have equally sophisticated measures for the malicious threats in terms of security, but you haven't mentioned that. Would you mind sharing what you have?
I'm not sure that this has increased the threats. The threats have always been there. When it comes to us dealing with threats from a reliability perspective, I've mentioned some of them. We've got what we call a safe rollout policy. We've institutionalized across Azure properties of the way that we roll out software in a way that's not going to be that way we can catch problems early. When it comes to security, I gave a talk at RSA conference just about 2 months ago on cloud security and what we do there to harden our infrastructure from security threats, not just for the infrastructure itself, but also to help customers get hardened against security threats like DDoS, for example, or compromise, letting them know they're vulnerable because they haven't patched their servers. So these are huge investments I didn't have time to get into.
Thank you.
I think there is one more question there. Hi.
Yeah, that's a great presentation. I want to understand when you deploy the smart NIC, how does the high-level software to understand to differentiate between server that has the smart NIC and the server that doesn't? Is the application software is transparent to them, and then you have an open abstract layer to shield that up?
So the question is, how do we know which servers have the smart NIC and which ones don't? This is something that we try to keep the information required for controllers on an as need-to-know basis. So many of the controllers aren't aware of what servers have smart NICs and not. One of them that does is, of course, the compute server, because the capacity of the server changes based on whether it's got a smart NIC or not, given the fact that CPUs have to be used if it doesn't have a smart NIC. When it comes to the SDN itself, that is largely the controllers are largely oblivious to whether it has a smart NIC or not, because the capabilities are the same whether it does or not. And so it's more of a capacity issue, not a functionality issue, as to whether one is there.
Okay, so I guess with that we will thank you again for a great talk. Really appreciate it.